So in these next couple of tutorials, what we're going to cover are titrations. We're going to revisit that type of technique, which we have done already, when we dealt with the types of reactions unit, a couple of units back. But what I want to do is just go through the different types that you can have. The type that we went over before are just strong acids and strong bases. Now I want to deal with, what happens when you have a weak base or a weak acid. Because you will see a change that occurs. So first, let's just review what titrations are. It's just basically a procedure or a technique that's used for determining the concentration of an acid or a base in solution by knowing the concentration of another acid or base within that same solution. With it, you're basically, just to review it, you're adding your titrant or whatever it is that you already know the concentration of, you're adding that to the unknown, and whatever amount of volume it takes to be able to get to what's called the equivalence point, that's what you'll use to be able to figure out the concentration of your unknown. Now, one thing that we didn't go over is something called the titration curve, which is basically a graph that plots the pH of a solution against the volume added of the titrant. So you'll be able to see, as you add this titrant to your unknown, what's happening to the pH. And from that, you can also, without using, if you remember, we used an indicator when we did the titrations. Without using the indicator, we can figure out, where that, the equivalence point is going to be, which is just a more accurate way of doing it. So here's an example of a titration curve. If you look at this closely, you'll be able to see that it's, in an actual curve, where at the very beginning of this, you're seeing a gradual increase in pH, as you're adding more and more, in this case, we're dealing with NaOH. So as you're adding more and more NaOH, you're seeing a very slight increase in pH. You are going to get to a point, though, where you'll begin to see a very sharp increase in pH, and that's where you'll see your equivalence point, and that sharp increase that you may see is, starts right here, ends right there, and then once that increase happens, then you start to level out again with pH. So you see a leveling at the beginning, you see a leveling at the end, and then in your middle you'll have your equivalence point. Which in this case, if you look at this, equivalence point is always going to be right in the middle of that curve. So whatever the pH is at that point, which in this case it just happens to be 7, that is where your equivalence point would be. Or another way of saying it is just where the number of moles of your acid equals the number of moles of base within that particular solution. Now, one thing that I want to show you is just, we dealt with indicators before. I want to show you how to figure out what the best indicator is, to be able to use with a particular titration. Which in this case, you can see that your sharp increase, on your titration curve starts at about pH of 3 and ends about pH of 11. So you want to have some indicator in the middle that's going to show your equivalence point. So it has to be between 3 and 11. Well, we can go and actually narrow that down even more. Where if you look at something called Bromcresco green, you'll see that it hasn't even reached the equivalence point yet, and it's already changing color from yellow to blue. So you don't want to have something like that because it's changing before you even reach your equivalence point. But if you look at something like phenolphthalein, you can see that with phenolphthalein, your color change is actually happening right near where your equivalence point is. It's colorless until it gets to about the 9, 10 pH range, around there. So you would want something like that, because then that will actually show you when you have more, in this case base, than you do acid, because you see that color change. So now let's just go through how to figure something like this out. In this case, you'll notice that you have 10 milliliters of 0.1 molar solution NaOH, you have 25 milliliters of 0.1 molar HCl, and you want to be able to figure out the pH of the solution. Now, if you look at the NaOH and the HCl, your equivalence point, again, as I was saying, is when the number of moles of the HCl equals the number of moles of NaOH in this case. Well, if you look at your numbers, you have 10 and 0.1 of the NaOH, and you have 25 and 0.1 of the HCl. Those don't equal out, so you know right off the bat that you haven't reached the equivalence point, so you're going to be actually finding the pH of the solution not at equilibrium. So because of that, you don't need to have an ice table, because you're not dealing with any equilibrium in this case. Now, because this is an at equilibrium, you are going to begin to notice that you might have more of one thing than the other. So we have to figure out which one of those it's going to be. So first thing I recommend is that you go and figure out the moles for each substance. So if you were to take NaOH, it would be 0.01 times 0.1, and that'll give you 0.001 moles of your NaOH, or another way of putting it is just OH minus. So now let's figure out the HCl. You have 0.025 times 0.1, so you have 0.0025 moles of HCl, or let's just go with H3 plus. Now, as you can see, you have more H3O plus than you have OH in this case. So you need to figure out how much hydronium concentration is going to be left once this reaction occurs. So the way that you do that is just by taking your 0.0025 and subtract the 0.001. That way you can figure out how much is left over. And from that, you're able to see that you have 0.0015 moles of H3O plus left over. Problem is, if we're going to deal with determining pH, we need to have this in concentration. So you have to have 0.0015 moles divided by some volume, which, just like when we dealt with buffers, you need to take into account the whole entire the total volume of that particular solution. So in this case, you had 10 milliliters NaOH, you had 25 milliliters of HCl, so that the total of that is 35, and so you'd have 0.035 like that. And that comes out to 0.0429. That's your concentration for HCl, or for if we're dealing with hydronium ions. So from that, you can figure out your pH by just doing the negative log. So if you do the negative log of that number, you're able to figure out that the pH of this particular solution is 1.37. So let's try another example, but before we do that, just to mention something, the first thing that you want to probably do when you're dealing with titrations is figure out what you have, whether you have a strong acid and strong base, or a weak acid and weak base, whatever it might be. That way you're able to figure out what type of titration calculation you need to do. So saying that, let's go through and see. In this case, you have 15 milliliters of 0.1 NaOH, you have 25 milliliters of 0.1 HCl. Both of those are strong, so you know that you can do the easier titration calculation, which doesn't deal with the ice table and everything else. So first thing you need to do is figure out how much HCl is going to be left over in this particular example. So you have 0.015 times 0.10, so you have 0.0015, and that's for the OH. Then you have 0.025 times 0.10, so you have 0.0025 moles of HCl. Subtract the two, and you're able to see that you have 0.001 moles of the hydronium concentration left over. So now you want to figure out the concentration itself. So now you have to divide this by the total volume. So you have 15, you have 25. That ends up being 40 milliliters. So if you do that out, you end up with 0.025 for your concentration for hydronium. Take the negative log of that, and you have a pH of 1.60. So again, that's the type of calculation that you need to do if you have a strong acid and a strong base.